Even though the reaction rate is controlled by a number of different factors, we're going to limit our the rest of the chapter's discussion to just how does concentration affect the rate of that reaction, and we're going to be doing a lab where we get to see that at work. So concentration and reaction rate are related, we learned, and the relationship between the rate of a reaction and the concentration of one reactant is determined experimentally. So the results that we know about this came about through experiments, and so our lab are going to come up with figure out the reaction rate for a particular reaction by actually doing that experimentally. And the experiment that we're going to do is actually going to be a series of experiments, and we're going to hope to reveal how the concentration of each reactant affects the overall reaction rate. So let's look at this particular reaction right here, where we have a hydrogen molecule reacting with a nitrogen monoxide molecule, and it forms a nitrogen molecule and water. Now, the initial reaction rate is found to vary directly with the hydrogen concentration. So this is through experimentation. They determined that the reaction rate is found to vary directly with the hydrogen concentration. Meaning that if I double the concentration of the hydrogen, then the rate of this reaction also doubles. Or if I triple the concentration of the hydrogen, it triples the rate of the reaction. So doubling the concentration, it goes twice as fast. Tripling the concentration of hydrogen makes it go 3 times as fast. So we can write a relationship between the rate of a chemical reaction. We're going to use a capital R for that. So capital R represents the rate of the chemical reaction. The symbol in the middle, it means proportional to. So the rate is proportional to the hydrogen molecule concentration. So if I double the right side, I would have to double the left side because they're directly proportional. The initial reaction rate is found to increase 4-fold when the concentration of NO is doubled. Okay, so for the other reactant, nitrogen monoxide, if I double its concentration, the reaction is increased 4-fold. In other words, it goes 4 times as fast if I double the nitrogen monoxide reaction concentration. And it will go 9 times faster if I triple the concentration of the nitrogen monoxide. So the relationship that exists there would be like this. The rate is proportional to the nitrogen monoxide concentration. So if in place of NO, I would put 2 because it's been doubled. The rate would be 2, and then on the outside I have the square right here. That square means, so 2 squared would be 4, so the rate of the reaction would be 4 times as fast. If I were to, in place of the nitrogen monoxide, put a 3, as it says right here, if I was tripling it, then I put a 3 in here, the 3 is squared, and the rate is now 9 times what it was before. So by looking at the numbers that I'm getting, the rate is always whatever the concentration is squared. Now, because R is proportional to the hydrogen concentration and to the nitrogen monoxide concentration squared, then it must be proportional to their product. So here's how we would write that. We would write it as R is proportional to the hydrogen concentration times the product times the nitrogen monoxide concentration, and it's squared. So we don't have an equation yet, but we have a relationship. So looking at this, doubling hydrogen on the right side would double the R on the left side. Instead doubling the NO, the nitrogen monoxide, on the right side would be double squared. R would now be 4 times as much. And so I can do other combinations with those and get other rates as well. So if I want to make this into an equation, I need to introduce a constant. And we're going to call this a proportionality constant into this equation. We've had this before earlier in the year when we were figuring out how much energy a electron had or a photon had. We had a constant in there as well. So if we introduce a constant in there, we would come up with this. So the rate is equal to the constant times the product of the hydrogen concentration and the nitrogen monoxide concentration squared. So now we have a rate law, or a rate equation, I should say, that represents how fast that reaction would go. And if I put in different numbers into this, I could predict the rate of the chemical reaction. So an equation that relates the reaction rate and the concentration of the reactants is called the rate law for that reaction. So we just wrote the rate law for the reaction of hydrogen and nitrogen monoxide. And this rate law, this equation, is applicable for a specific reaction. In other words, that rate law doesn't fit any other reaction, and it only works at a given temperature. So if I had raised the temperature, the K would become different. Okay, so the value of K usually increases as the temperature increases, but the relationship between the reaction rate and the concentration is almost always the same. In other words, the only part that would change about that equation is that we'd have a different K if the temperature was different. So we can come up with now a general form for the rate law, and it's given by this equation. So R is equal to K times A, which is the first reactant, raised to some power, and then B, the other reactant, raised to its power. So the rate law is applicable for a specific reaction at a given set of conditions and must be determined from experimental data. So when we come up with our rate law for our experiment, we're going to have to do the experiment and gather data so that we can write the rate law. And the power to which the reactant concentration is raised is called the order of that reactant. So in this equation up here, the N up here for A is the order of A, and the M is the order of B. So whatever coefficient whatever power we put up there, that is the order of that particular reactant. And so the value of N is said to be the order of the reaction with respect to A, so that the reaction is said to be like the nth order of A. So whatever N is, like it could be the 0 order, first order, second order, like that. Now, an order of 1, in other words, if we use an exponent of 1, a power of 1, means that the reaction is directly proportional. So this is something probably important to remember as we go forward, that if you find out that two things are directly proportional, then you have determined that the order, the power that I put after that reactant is going to be a 1. An order of a 2, in other words, if I use a power of 2 after the concentration of that reactant, that means that that reaction rate is going to be directly proportional to the square of the reactant, like we had for nitrogen monoxide. We found out that whatever I did to the concentration, I squared that, and that was how many times more the rate. Now, if you have an order of 0, now you might wonder, why would we have that? But we have discovered in doing experiments that there are some reactions where one of the reactant doesn't cause the reaction rate to change as long as some of that reactant is present. So if you ever should see that in one of our examples that we will cover this through the end of this chapter, that where you have one reactant and it seems like the concentration rate just stays the same no matter, the reaction rate just stays the same no matter what concentration I use, then you will put a 0 after it. And you know from math that any number raised to the 0 power is 1. So it's in essence, you are just multiplying by 1. So a 0 power just means it doesn't depend on the concentration. You just have to have some of it present. Now, after you have written your rate law and you have all the powers up there, the orders of each of the reactants, if you add up all those powers, you come up with what's called the order of the reaction. So the other one was the order of the reactant. This is going to be the order of the reactant, or the overall order. You can ask it or say it two different ways. So in this particular reaction right here of nitrogen dioxide reacting with carbon monoxide, forming nitrogen monoxide and carbon dioxide. Okay, and they've discovered that the rate law for this particular equation is R equals K times the nitrogen dioxide concentration squared. Notice that there's no CO in there. And so that one is a second order of the reaction for this particular reaction is going to be the second. So it has a 2 after it. There's nothing else to add to it, so it's just a 2. Now, what it meant was even though you could have written it with right after the NO2 concentration squared, you could have written in brackets a CO in with a 0 power, but it means 1, so quite often we just leave it out. But it would not be wrong to write that after it, but it's a 0. So the K that we had in our previous equation is a specific rate constant, and it's the proportionality constant that relates the R on the left side with the concentrations on the right side. And once the reaction orders or powers, in other words, those little numbers that you have as exponents after each concentration, once you know that, then you can actually calculate the value of K. And what you use for that, you would use numbers that you had recorded or gathered by doing an actual experiment. And the value of K is for a specific reaction. As we've said, it doesn't fit any other reaction, even if those reactions are take place under the same conditions. It does not work. So each one's very unique. Now the units of K are not always the same. This is the part that's maybe a little bit confusing for some students. Is up till now, when we had a constant, it had always the same units. Well, in this particular situation, the K, the units for it depend on the overall order of the reaction. So we have to look at one of these rate laws to be able to figure out what the units are going to be. So the value of K does not change for different concentrations of the reactants or the products, and so that the value of K for a reaction remains the same throughout the reaction. In other words, the K doesn't start out at one value when there's a lot of reactants, and it doesn't change to something else because there's a lot of products. It doesn't change throughout that whole time. So K is constant through this whole reaction. And the value of K is for the reaction at a specific temperature, as we've stated, just to make sure that's clear. And if we increase the temperature of the reaction, the value of K would increase. I'd have to do the experiment all over again under these new set of conditions. And the value of K changes, becomes larger, if you have a catalyst present. So just by adding a catalyst, the K becomes a different number, because remember, a catalyst will cause the energy pathways to possibly be different and form different activated complexes and things like that. So that would be altering the conditions, and we'd have to have a different value of K. So K is very specific. Now tomorrow we're going to be looking at some sample problems where we get to take data gained from an experiment and determine the rate law for that particular experiment based on the concentrations of the reactants that are used. So that's for tomorrow.